Good afternoon, everyone. Uh, so today is the second lecture for this topic, quantum clocks for fundamental science and metrology. So last Wednesday, Tuesday, I think it was the first lecture where I was giving an introduction about the atomic clocks, and also I explained about the cesium clocks, microwave clocks. So today in second lecture, I will be talking about the optical atomic clocks. I mean, last time I explained the difference between microwave and optical atomic clocks. So today we will focus on optical atomic clocks, which are actually much better in terms of accuracies compared to the microwave clocks or cesium clocks. So I will be covering three parts. One is some basic introduction, and then there are two different types of optical clocks. One is based on single ion, and other ones are based on neutral atoms. And I will be discussing in detail about both type of these clocks. So to start with, let's just look into the present accuracies of the optical clock. So the plot what you see here, this x-axis is the years and the y-axis are their fractional accuracies. That means delta t by t or delta nu by nu, both are same. And these green dots are actually fountain clocks. And that I was also showing in my last lecture, and they have reached to some sort of 10 to the power minus 16 order. Whereas the other ones, this cyan and this yellow discs, they have reached to much better accuracy compared to these green ones or the microwave clocks, and you see they have reached to an accuracy level of 10 to the power minus 21. So that is something like five 4 to 5 orders of magnitude better compared to the microwave clocks. So at present the optical clocks are the state of the art atomic clocks. So, just to begin with, let me give you an example. So we know that until, let's say, 50 years back, the definition of time was based on rotation of the Earth, or actually, even at that time, it was based on year, like one topical year. So the Earth is rotating around the Sun, and it takes so many seconds, as you see here, so many seconds, and 1 second was divided by 1/1 year. That was the definition until 1967. And even before that, before 1960, it was based on rotation of the Earth. Like Earth takes 24 hours to rotate around its own axis, as you see here the picture. So the video, and that was the basis for measurement of time universally. But let's say, why do we go to the atomic clock? So as I told you that the present based atomic clocks are accurate, fractional accuracy is something on the order of 10 to the power minus 21. Let's say if you have to build an such accurate clock based on the rotation of the Earth, that means there in that case you have to measure the rotation of an Earth with an accuracy of 10 to the power minus 18 degree, which is in the present level of technology, it's just impossible. It's not possible. So 18 orders of magnitude smaller than 1 degree. That's just impossible. So it's not possible. So what can you do then? You can take an oscillator which oscillates very fast, not like very slow moving thing like an Earth. So which oscillates something like, let's say, some 10 to the power 18 times or so, 10 to the power 15 times per second. And then you can make such a better accurate. That is the basis actually to make a more accurate clock. So basically, in a nutshell, what I'm trying to say, if you have to make a better clock, you have to take a faster oscillator, and that's what is the quality of a clock. It's defined by Allen deviation. So smaller the Allen deviation, it says deviation. So smaller the basically deviation, it's better the clock. And it has two parts. One part is this delta nu by nu zero, where nu zero is the central frequency that you wanted to measure for an atomic clock, and delta nu is its line width. So you see that it's inversely proportional to nu zero, and that means if you take an oscillator which is oscillating much faster, nu zero is higher and higher, you can actually make better and better clock. So your deviation will be much smaller. That's the basis why we want to go from rotation of Earth to an atomic clock. Or even like from microwave to optical clock, because in the microwave the frequency is something on the order of 10 gigahertz, whereas in the optical it's 10 to the power 14 to 10 to the power 15 hertz, so 4 to 5 orders of magnitude better, and that's actually giving something like 4 to 5 orders of magnitude better in terms of accuracy for the optical clock with respect to the microwave clocks or fountain clocks. It has a second part, which is, let's say, the statistical accuracy of the clock, and it is 1 over square root of n times c. Here c is not the velocity of the light, but c is actually number of measurements. That's what is written in. And n is number of samples. So basically, if you have more and more samples, then your statistics become much better. So that's what it means. Or if you have more and more measurements, your statistics also becomes better. So that means your clock can be more accurate if your number of samples or number of measurements are very high. That's what it means. Okay, so now let's look into some fundamental of the optical clock. So basically, the optical clock is, as I explained last time, particularly for any clock, it is any atomic clock. Basically, you have to measure this nu zero. Nu zero is the frequency of an transition, very accurate. So for optical clock, basically you also have to measure some optical transition frequency. Now there are different type of optical transition frequencies. You have to choose a transition which has a very narrow line width. So that means delta nu is very narrow. As you have seen last here, like if delta nu is smaller, so you can make a better clocks. Yeah. So you have to choose a transition where delta nu is very small, and that means you cannot choose an electric dipole transition which has a much wider line width, typically few tens of megahertz, but you can choose some classically forbidden transitions. For example, electric quadrupole transitions or electric octopole transitions, or there are another type of transitions called hyperfine induced transitions. These are classically not allowed, but through quantum mechanics they are allowed, and these transitions can be driven. So so here you see, like probably in your textbook things you have written the matrix element for electric dipole transitions, which typically all of us read, where this element is charge times r, but here it is, you see, it's r square, or it is r to the power 3. So this is actually Wigner-Eckert theorem. And for example, the selection rules, what you read in your standard textbook is delta L is equals to 0 plus minus 1, or delta S is equals to 0 plus minus 1, all these sort of selection rules. But for these transitions, like forbidden transitions, the selection rules are also different, and they come from Wigner-Eckert theorem. You can go back and look into those things in detail. So these are classically forbidden transitions, but quantum mechanically they are allowed, and as a result of that, they are very narrow. So instead of tens of megahertz, their line widths are nanohertz or millihertz. So that means they are also, you gain by several orders of magnitude in terms of accuracy. So practically speaking, for not that any optical transitions will be very helpful to build a clock, but you have to choose the transition which has very narrow line widths. Okay, so once you have selected the transitions, which actually is for some atomic elements or ionic elements. So as I already pointed out, there are two type of optical clocks. One are based on neutral atoms. So you can take some neutral atoms which has this sort of highly forbidden transitions and can make a clock based on that. I will come into detail how that works. For example, here you see these are like strontium atoms, which are in a magneto-optical trap. In my last lecture, I was explaining what is magneto-optical trap. So these are strontium atoms, which are confined in a magneto-optical trap, and people build atomic clock using those, let's say, billions of neutral strontium atoms. The other one is ion. Instead of neutral atoms, singly charged ions can be also confined in an electrodynamic trap, and detail I will discuss in this lecture later. and that you can confine in an ion trap, and you can build a clock on that. So the principally it's same, it's only atoms or ions, and then you drive the clock transition and you measure this nu zero very accurately. The only difference is, well, of course, ion and atom, these are different, but only other major difference is, in case of neutral atoms, you have multiple atoms, like 10 to the power 6 or 7. Whereas in case of ions, you have only one ion. So that means if you remember the systematic slide that I was showing, it's 1 over square root of n. So your n is much larger in case of neutral atoms, but n is only 1 in case of ion. Yeah, so your signal to noise is very less in case of ion. However, the number of measurements can be very large in case of ion. So C, what I was writing C, that could go very high because ions can be trapped for very, very long time. So since it can be trapped for very, very long time, you can do multiple measurements within that time. So that's how we gain. Okay, so before I start explaining how this neutral atom clock or ion clock works, let me just tell you a little bit brief about the optical clocks. Those are available in different parts of the world. So some of the developed countries, in fact, all the developed countries have already built these optical clocks in their national laboratories and so on. So here you can see a mapping where these for example, NIST, National Institute of Standard and Technology in USA, they are pioneer in making clocks, basically atomic clocks. In fact, the idea came from there only. So they have based fountain clock, they have based optical clock and everything. And they have all sort of iron clock, atom clock, everything here, what you see. In Canada, also in NRC, National Research Council in Canada, they also have a strontium neutral atom optical lattice clock. In Europe, Germany, France, Italy, UK, they have already built very high quality optical clocks based on neutral atoms as well as ions. Japan is another place. Actually, this neutral atom optical clock, this concept came from Japan, from Hideyoshi Katori's group. So he first proposed that that's how we can build a very good quality clock. So that's why Japan is actually pioneer in making optical atomic clocks, and they have several of them. Australia, they are coming up. They are trying to develop. Like India, they don't have any operational optical clock now. And in India, there are 4 laboratories. One is in NPL, National Physical Laboratory in Delhi. In Pune, actually, at IUCAA, in my lab, and also ISSAA Pune. Both of us are building optical clocks. For us, it's based on ions. For ISSAA Pune, they are building strontium neutral atom-based optical clock, and we have a science plan. That's why we actually choose, both of us choose 2 different elements, and then it will be connected. Anyhow, that's not so important at this point. And in IIT Tirupati, also one faculty, he is coming up and trying to build a calcium ion-based clock. So, but none of these places, they have an operational clock. All of us are just trying to build the clock at this moment. Okay, so now let's begin to understand in more detail how these 2 type of clocks work. And to start with, let me just explain this ion clock. So this is a pictorial view where this is a single ion which is trapped here, and what you see here, these are actually electrodes which electric fields are applied to these electrodes, and that produces a trapping, a confinement thing, and ion is confined within that confining potential. And this rest of this purple color and red color things are actually lasers which are used for laser cooling. So these electrodes are confining the ions, but then still the ion have a lot of thermal energy. You have to cool it down to microkelvin or some hundreds of microkelvin temperature, and that is done by laser cooling. And laser cooling, what I already explained in my last lecture. So it's the same principle. So laser cooling principle is same, doesn't matter whether it is ion or atom. However, the confinement, the way of confinements are different for neutral atoms and ions. For example, in ion, it is an ion trap. I will explain how it works. And in atom, it's a magneto-optical trap or optical dipole traps and etc. So once you have this ultra cold, not ultra cold really, actually cold, hundreds of microkelvin ion, then you shine the clock laser to drive the clock transition, and you measure fluorescence with respect to its frequency and etc. And you find out what is this nu zero and delta nu. Okay, so now let us understand in more detail about this. So this ion trap was actually developed by these three like stalwarts. So first, the ion physics, like ion producing and those things, were started by Penning. He's a Dutch physicist in Leiden, I think, University of Leiden. He first produced ions, photoionized, and so on, so on. And then later on, Wolfgang Paul and Hans Demelt, they created these ion traps technically. Technically, they produced these ion traps, and they produced in two different ways. One is named after Wolfgang Paul. It's called Paul trap. Another one was developed by Demelt, but he named it in the name of Penning, and it's called Penning trap. Two works in a different way. I will discuss that. So, and these ion traps have several. It's a very important tool in today's world. Probably you know about quantum computers and etc. So there are quantum computers, the most accurate, or let's say most at present the working quantum computers are based on trapped ion. And this is what this technique, ion trapping, is actually used for confining these ions and then making them for the quantum computers. Okay, today we will not discuss about quantum computers. Let us focus on clocks. But basically, the same or similar ion trap is also used for optical clocks. So ultimately, it's basically confining the ions. Yeah. So let us try to understand. So, and we will be discussing about mostly Paul trap, because that's what we are going to use it for, the optical clock purpose. And I will tell you why that is the case. So let's just start with a simple thing like equation of motion. And this is like a force balance thing. What you see, m is mass of an ion, r double dot is the acceleration, and it's balanced with respect to an electrostatic force. Q is charge and E is electric field. Now this E you can write as a negative gradient of the potential, electric potential. We know that, it's a very simple thing. And now if you take this form of this potential quadratic to spatial positions, like let's say it's an radially symmetric potential. Radial means x and y direction, and z is the vertical axial directions. So if it's a radial symmetric, that means x and y directions have the same nature of the potential. That's why it's minus alpha. Alpha is a constant times x square plus y square plus beta. Beta is another constant times z square. Yeah, so it's a quadratic form of the potential. I will tell you why that is the case. Then if you just do this little math, then basically you will see the force along the x and y directions is equals to there is this negative sign, so this negative sign cancels alpha times x plus y, whereas along the z direction it's minus beta times z. Now see, if the potential has this form, then the force is proportional to position of the ion. So that means if z is equals to 0, so x, y, z 0 means that is the confinement point. If the ion is moving away from the confinement point, for example, if z increases, that means the ion feels more force to come back. That's why this negative sign is here. So as the ion is away from the trap center, it receives more force to come back, to push it towards the trap center. That's what is needed. Like if I am confined in this room, if I am like going out of this room, somebody have to push me more so that I can come back to the room. That's what it means. Now here in the xy direction, you see this is a plus sign, so it won't work. That means as it is going away from the x is equals to 0 and y is equals to 0, so it will feel more force to be pushed out. So that means by this simple thing, we can get confinement along one direction at a time. X and y, let's say it's r, so that means either I can get confined along the z direction or I can get confinement along the xy directions, but not both at the same time. And that's what comes from the Earnshaw's theorem. So basically, there is a saddle point. If you know the maxima minima finding out, there is also one thing called saddle point. So basically, in this kind of electrostatic potential, you can get a saddle point, but there is not a global minimum. There is a local minimum, and the potential sort of looks like that. So, for example, if this is the z direction, then along the z direction there is a local minimum. So it's confined along this direction. However, along these directions, along r direction, it's a maximum. So it is not confined. So ion will fall from this side or fall from that side. So this potential some sort of looks like this uncle chips, potato chips. Yeah. So I always take this example. So basically, this looks like a potato chip. So the ion can be trapped here along one direction, but they are not trapped in the other direction. So it's not good because we have to confine the ion in all three directions. So what are the possibilities? And that possibilities, these two guys, Demelt and Paul, they give two different solutions to encounter that problem, and that's what are named as Penning trap and Paul trap. So in Penning trap, what happens? See, this is the potential. They apply some magnetic field, and as a result of magnetic field, the ion will experience a cyclotron motion. You know the Lorentz force Q times V cross B. So ion will basically rotate within that potential, and if you apply the magnetic field like inadequate magnetic field, then this spinning motion of the ion will be very fast. So as a result, what will happen, whenever ion will try to fall from this direction, it will basically move and it will see this very high hill, so it won't be able to fall. Then again it will move to here and it will try to fall from the other direction, but due to the cyclotron motion it again moves and it will see this high hill. So that basically you have to spin the ion very very fast so that it doesn't fall. Yeah, and that is called Penning trap. That was the solution given by Penning. So an electrostatic force plus a magnetic field. Whereas okay, this is how the axial motion looks like. And in a Paul trap, what happens, instead of spinning the ion, you basically rotate the potential. So instead of an electrostatic force, you apply an AC electric field, an alternating electric field. So what will happen, so once you see this confining potential along this direction, and immediately after half of the time period it will alter. So your confinement will be along radial direction and axial direction will be deconfinement. That's what you see here in this video. So this is exactly what happens in a Paul trap. There you do not apply any magnetic field. Instead of electrostatic field, you apply an AC electric field. And that also in both cases, on an average, the ion will feel a 3D confinement, a three-dimensional confinement. Now, for optical clocks, we actually always use Paul trap, but not Penning trap, because in a Penning trap, people have to use a magnetic field, and in a magnetic field, the energy states of the ion will feel a shift called Zeeman shift. But that's not what we want, because we want to measure the frequency difference between two states very, very accurately. Now, if they are shifted due to the Zeeman shift, that means you are not measuring the actual transition frequency, but you are measuring the shifted transition frequency, which we don't want. So that's why, since Penning trap uses a magnetic field, we don't use that. We use Paul trap. Okay. So since that is the case, let us explain a little bit more about the Paul trap, since basically we are more focused towards the clock business. So in a Paul trap, what happens? The potential, this sort of pole of the potentials alters, and that's what you see. So these are basically electrodes, and the electrodes becomes high, low, high, low, high, low. So opposite electrodes. So basically this is a radial symmetry. So this is a cross section what you see. So you can consider this is a ring and this is a ring, and then you just cut it so that you are seeing the cross section. So basically this electrode and this electrode is same, it's just cutted, and similarly this one and this one. So due to this alternating potential, it will be high, low, high, low, high, low, and that's what is shown here in a video, and ion will be confined in this way. And due to that, the resultant force will be also confining, deconfining, alter, and it happens very fast. How fast it is? It's on the order of, let's say, 20 megahertz. Like so a few microseconds. The time period of the oscillations are on the order of few microseconds. So over every few microseconds, it will alter, and as a result, ion will basically stay there. It will feel that I am confined. And the form of the electric field, what is? It's some sort of small DC electric field. Forget about that part at this moment. Why that is the case, and the alternating electric field. Now let's look into this. Now let's come back to this equation of motion again with this sort of potential where you are using this AC electric field, alternating electric field, and this is I'm just writing the equation of motion. So R double dot is basically is written here, and then instead of writing it in this so ugly way, I am just writing x, y, and z as just u. Yeah, and then there are two parameters. One is a, q, and actually tau. And this a, q are dimensionless parameter, not constant. Sorry, dimensionless parameters. A depends on DC value of the potential. As I said, that it has a DC part and it has an AC part. So A depends on DC part of the potential, and since it's a radially symmetric, so along the x and y directions, value of A is same, and along the z directions, it's factor of 2 higher. It's just because why do I have these things? Yeah, there is a factor of 2 in this form of the potential. And similarly, Q depends on V, AC part, AC magnitude of the AC potential. And tau is omega times T. It's like basically omega is 1 over time period. So again, it's also a dimensionless thing. T is actual time and omega is the time period, half of the time. Actually, omega is the inverse of the time. And then if you do the mathematics, which we don't need to do at this moment, then the solution will come in this form, where this A and B are some constants, which depends on the initial condition of the trapping. And then it depends on this beta and these coefficients, which beta depends on basically this A and Q parameters. We'll come to that in the next slide. Now, since everything, this alternating potentials is altering very fast, the ion will actually not lose its energy. And it's basically an adiabatic process. That's what I wanted to mean. And for that, the values of the A and Q have to be much, much smaller than 1. It's a dimensionless thing, but it has to be much, much. So you have to choose the A and Q values so that it's much, much smaller than 1. And beta, which depends on this A and Q values, also have to be much, much smaller than 1. Now you can, if you are more interested, you can go back and do all these maths, but that's not really the detail of the math. That's not really necessary at this point, and also not possible, because then each of these math will take 1 classes. Then if I put all these values here, then a trajectory of the ions can be written in this form, where this is like Q and beta, as you see here, and then omega is the time period, and there is this cosine function and there is this cosine functions. So this is sort of a, you can say, an envelope, and then it's modulated. Yeah, we know these things like this frequency modulations and all these things. So they give this kind of multiplication of the cosine factor, cosine A, cosine B, and that's what you see here basically. Now, if I want to see what is how this trajectory looks like when the ion moves in this sort of potential, and this is actually not animated, this is actually computed things. So that's how the trajectory looks like. And for some certain parameters along the x and y direction, path of the ions in this oscillating potentials are like that, where this blue one is the z direction and the red ones are the x direction, and they will have a factor of 2 difference in amplitude because of the nature of the potential. And if you look closely, then it has two different motion. One is this motion, which is much smaller, much slower, and this is modulated by a very high frequency motion. If you zoom it in, then you see these high frequency oscillations here. And what is basically plotted here after separating out from these slow motions. Actually, the slow ones is called secular motion, and these faster ones are called micro motions. So secular motion depends on temperature of the ion. So as you see here, the ion is moving. If the ion has more thermal energy, it will move much farther away from the center of the trap. Yeah, and that's what the secular motion amplitude says. So this vertical direction is the amplitude, how far they went from the trap center. So if the temperature of the ion is more, they will move much further. Whereas the micromotion depends on the AC part, that AC electric field that you apply. That's how it modulates the secular motion, and their amplitudes are much smaller. But that's very important thing for building a clock. Okay, now there are different geometries that one can think of to make a pod, make a trap, ion trap, and these geometries are basically electrode geometries. So, for example, this is one geometry where the electrodes are in hyperbolic shape, and then there is another electrode which is in a ring shape. Then this was modified to a linear trap where these are like some linear rods, copper rods, and like the RF is applied between these and these two electrodes, and it alters diagonally. So basically, diagonal electrodes have the same potential at any instant of time. So sometimes these two diagonal electrodes have the same potential. Sometimes these two diagonal electrodes have the like opposite and each other. Then this one was further modified to this kind of trap where this is like a two electrodes and this is there is a ring electrode, and then also there is another one called end cap trap which looks something like that. So this ring is basically broken into two parts. You can consider this ring is broken into two parts, and then they are made coaxial to this electrode, and that's how this is made. This is easy way to understand that. And advantage of this sort of this last one end cap trap is because you have lot of optical access, because you need to apply several laser beams for laser cooling and exciting the clock transitions and so on. What you can see there, you don't have that much of access, but here you have a lot of optical access. So that's why this is more user friendly, let's say, compared to all the other geometries. So now let me explain you the trapped ion optical clock in a pictorial way. We have now gone through the equations and so on. So as I said, for this kind of trap, if you look very closely to this part, then that's how it looks like. So this is one electrode, and these are the coaxial outer electrodes. And then first you have to produce the ion. So, but you cannot. How do you produce it? You can just take an atomic. You can take some bulk sample of the ytterbium atoms, let's say, because we are building ytterbium. So I am taking this as an example, and then you heat it up. And due to this diffusion process, ytterbium atoms will come out of the oven. Ytterbium atoms will slowly start coming of the out of the oven. But these are neutral ytterbium atoms. They are not ionized. So first thing is you have to produce singly charged ytterbium ions from these neutral atoms, and that is done by photoionization process. So you apply basically enough UV light, and then you strip out one of its valence electron. Ytterbium has two valence electrons. You just strip out one of them, and then it becomes singly charged ytterbium ions, and that process is called photoionization process. I think probably all of you know about that. Like basically, it's a you apply photons to strip out the electron. Then you apply adequate electric field to this to these electrodes, and adequate electric field means that these A and Q parameters have to have Q and beta parameters have to follow certain rules and etc. That's what adequate means. If you apply the adequate electric field, you will be able to produce the right electric potential for confinement, and then you will be able to confine some of the ions. Okay, so you confine some of the ions, but as we said that for ion trap we have to use only one ion. We cannot use multiple ions. And the reason is if you have multiple ions, then there will be a Coulomb repulsion between among these ions, since these are charged particles. And due to these Coulomb repulsions, again the actual clock transition frequency will be shifted, which we don't want because we want to measure the actual unperturbed transition frequency. So that's the reason why for ions you have to use only single ion so that there is no Coulomb repulsion. Whereas for the neutral atom that is not the problem because there is no Coulomb repulsion, so there is no such shift in this case. So okay, fine. So we have to then get to one ion, single ion. How can we do that? So we'll just okay. So first of all, we have to detect the ion. So what we do, we apply some laser frequency, and we detect the fluorescence out of it. And let's say there are some n number of ions. This n for my example case is 4, and that 4 number of ions produces some level of fluorescence. Let's say this is this one here. Now you just decrease the electric field potential a little bit. Now as you decrease the electric field potential, all 4 ions will not be able to stay there because they already have Coulomb repulsions. So they will feel, okay, I'm not able to stay in this potential, so some ion will leave out of the potential. So it's like a cup. You have 3 things. If the cup size is smaller, if you make the cup size smaller and smaller, then all the balls will not be able to stay within the same cup. Something will fall. Exactly, that's what happens here. Then as one ion leaves, the fluorescence level will also come down. Yeah, and you keep on doing these things, then basically you will, in the fluorescence, in the detector, you will see these steps. It's going one to other, and then at the end, when you have no ion, it's just empty, then you will basically see the background count. So this way you actually calibrate your system. Next time you load the ion and you just stop here. Now you know that this is the step, so one ion means this one. So I have one single ion. Also, one can use a this EMC, a CCD, to actually image these ions, very high resolution imaging systems, because these ions are very close to each other, and then also image it. But actually, one have to do both of these things, because none of this, I mean, if you have only one, it's not reliable enough. So you have to have both of them so that it's highly reliable that you have only single ion. Otherwise, your clock accuracy will be completely will go wrong. Okay, now once you have the single ion, you have to cool it down to some sort of tens or hundreds of microkelvin temperature, and you have to apply adequate lasers, which is for this laser cooling technique. I already explained laser cooling, so skipping the details. And then the ion will lose its energy. But then actually what happened, we are talking about micron level precision, 1 micrometer level of precision. And it's very highly unlikely that it's very difficult to align. I mean, if you don't do anything extra, it's very difficult to align the crossing of the laser beams with the ion. So you need to have some extra knobs so that you can change the position of the ion little bit in micron level precision. For that, we have to add few more electrodes so that you can push or pull the ion little bit as you want, and then basically bring coincide the cross section of the laser beams with the position of the ion at micron level precision. And that is done by these radial electrodes. Then once everything works properly, then ion will be actually cooled to microkelvin temperatures. And then once it is at that temperature, you have to shine this clock laser to drive the optical clock transitions, and then do the measurement, and basically then you can make the actual clock. Okay, so now we have understood how, in more or less, let's say, detail, how the ion clock works. Now we are going to neutral atom clocks. As I said, so neutral atom is another very important area where one can build a very accurate clock. And this is a pictorial representation of the neutral atom clock. And what you see here, this red ones are the magneto-optical trappings, laser lights, and this blue one is the optical lattice or dipole trap things. And these are magnets. So I explained how the magneto-optical trap works in my last lecture. So I will be explaining this optical dipole trap and optical lattice in this part. I'm assuming that you already know the magneto-optical trapping, because that's what I already did in the last lecture. So here the difference, as I already said, that you have multiple atoms, several. So instead of one single ion, since you have multiple atoms, your signal level is very good in this case. So let us first understand optical dipole trapping, because that is one of the fundamental basis for building the neutral atom optical lattice clock, even for the optical lattice also. So here what happens, if you look like a laser beam, which is, let's say, focused. So that's what you see here. So this violet one is a laser beam which is focused by these lenses here. And at the focus, if you consider it's a single mode laser, like electromagnetic mode is 0, 0, no higher order modes, then the intensity distribution is Gaussian. So intensity distribution in this cross section is Gaussian. The intensity distribution, how it looks like, is something sort of that, and it's a Gaussian profile, and that's what is written here is a Gaussian profile. Now there is a lot of energy, lot of the laser power, which will actually shift, which will perturb the energy levels of the atoms, which are here, and this shift is due to basically Stark shift. Yeah, you know Stark shift. Like laser has it's an electromagnetic wave, so it has an electric part in the wave nature, and this electric field will interact with the atoms and will produce a Stark shift. Sometimes it's called also light shift in this case because it's induced by the laser. So the Stark shift Hamiltonian is like induced dipole moment times electric field. So here in this case, the electric field is the electric field part of the electromagnetic wave. And the shift of the energy levels can be written as this Hamiltonian square, like this matrix element square. And since it's in terms of energy, it's divided by h bar times delta. Delta is the detuning from the resonance point. And basically, you can see the shift which is proportional to omega square. Omega is called Rabi frequency, and Rabi frequency is proportional to intensity. So in a nutshell, the shift of the energy level is proportional to intensity of the laser. Now intensity has a distribution at this focus point. So that means shift of the energy levels will also have a spatial dependence. So that means if the ion is here, it will have the largest shift, sorry, not ion, atom. If the atom is at the center of this Gaussian beam, then it will have the largest shift, whereas at it goes out of the center, then the shift will be smaller and smaller, and that's what you see here. And these shifts will happen into both of these states, which are associated to the clock transition. Let's say one ground state and one excited state, and the amount of shift will be different. Amount of shift will be different because both of these states have different polarizability. It is D. It depends on polarizability. So depends on the difference polarizability. This amount of shift will be different, but both will have this shift. Okay, so far so good. Since it will see a spatial dependent shift, basically it will effectively produce a confinement, a potential which is spatially dependent. So here at the center, if I consider it is at x, y, z is equals to 0, so this is actually a potential which has a lowest energy at this point, and it is increasing this side and this side. That's what exactly what you see here. So basically atom will try to minimize its energy. So that means atom will always try to be here. As it goes away from this point, it will always try to minimize its energy and tries to come back there. So it's essentially a confinement. So if I consider this position where the energy level shift is maximum or the potential is minimum, then that is my confinement point, and it will sort of produce again a quadratic form of the potential. So it's called electric dipole potential, and that is again having quadratic nature, as we have also seen for the ion trap. So for any trapping, actually, even if you remember, for magneto-optical trapping, also finally we want to produce a force which is linearly proportional to the space. As it is away from the center, away from the 0 point, it gets more force proportional to its shifted position so that it can come back. So force is proportional to its position basically with a negative sign. And with this kind of potential, we can also basically produce the same thing. If you take a gradient, then it's just proportional to R or Z. Yeah, and that's what force is. Now, so far so good. We have learned the dipole potential. Now, what happens if you take a counter propagating laser beam? So far it was only one laser beam which was focused. Now let's say I put a mirror and I reflect it back. So that means I have a counter propagating laser beam. So two laser beams which are coming from opposite sides. And then what will happen? It will produce a standing wave, because both of the laser beams have the same phase and frequency. So it will interfere and produce a standing wave. And if you imagine sort of how it looks like, it will just produce pancakes. Yeah, so it will produce these parallel pancakes. And then due to this standing wave, it will basically create this sort of potential, and like an how do I call it, a periodic potential. So not only one of them, but it will produce periodic things of the light shift, or periodic optical potentials, optical dipole trap potentials. So instead of only one, which I described for the optical dipole trapping, you will have several of these things. Yeah, and the depth, but just by doing a little bit of more math, as I said already, it will be proportional to intensity of the laser, and it also depends on polarizability of that state. So that will be the trap depth. So if you produce more intense laser, it will be having more trap depth, so you can confine many number of atoms, or let's say like that. And how it looks like, so these are like all pancakes, as I told you, for if you consider just two counter propagating laser beams, and then this will be like array of these quadratic potentials where the atoms can be trapped. If you now think about that potential, nature of the potential in 3 dimensions, I think all of you have seen egg curtains. So exactly it will look very similar to egg curtains in 3 dimensions. So the egg curtains are like periodic nature of the potential, where the eggs are basically neutral atoms which are trapped. So that's what you see here, these egg curtains, and where the eggs, for example, are the neutral atoms. So you can artificially, using lasers, you can create these egg curtains, and then you can trap multiple atoms in that in sort of artificial egg curtain. Okay, now you have trapped multiple atoms in which are equally spaced in a actual in your experiment or in your setup, where that can be finally used for producing the optical clocks using neutral atoms. But still there is another last problem, that is, these to produce these egg curtains, you are actually using very high power lasers. The typical power is, let's say, 20-watt laser beams, which are focused on something like 50 to 100 micrometer distance. So basically, the size of the egg curtain is 50 micrometer, not this big. So we are talking about egg curtains which are like 50 micrometer by 50 micrometer in size. Okay, and there you are creating by very high power lasers. No, that will again produce light shift, as I explained. So energy levels of the clock transitions will be shifted due to these high power laser beams, and that's what, like Stark shift. That's what you see here. Like excited and ground state, they will be shifted from its clock transition. So basically, that will not allow you to measure the actual transition frequency. That's not very good. That's not what we want. So then there is another thing which was found out, and that is exactly was found out by Hideyoshi Katori's group in Japan, and they first gave this idea. Okay, let us use a laser beam at a particular wavelength where shift of the different energy levels will be equal in magnitude and in same direction. So as a result, what will happen? The total shift between two energy levels will just cancel each other, and that sort of wavelength of the lasers are called magic wavelengths. So let us try to understand that last part a little bit in more detail. So as I already explained, like if you are using very high power laser, then these levels will be shifted, will be perturbed from its original position, and that's due to Stark shift. Now, if you look into the polarizability expression, then polarizability due to multiple expansion, basically, it will have several terms. And the terms are, one is scalar polarizability, then vector polarizability, then tensor polarizability, and so on. And that depends on wave functions of this state. So this polarizability depends on wave function of different states. So for different atoms, for different energy states, the polarizability components are different. It also depends on quantum numbers like M, J, G, J quantum numbers, M quantum, how these basically are coupled, like electrons are how they are coupled with the nuclear spins and so on. So that means basically if you now look into two different energy levels associated to the clock transition, then these numbers are different for two different states. So their shifting will be different. So as a result, the shift not necessarily will be in the same direction or in the same in magnitude for two different states. And that's what exactly I told you. We have to find out some particular wavelength where these shifts are exactly cancels each other. Yeah, and that's called magic wavelength. For example, as you see here in this picture, so this is the original states and this is the original clock transition, and these dotted lines are shifted clock transition. But amount of shift for this state and for that state is exactly same and in the same direction. As a result, this shifted clock transition frequency is same as the original clock transition frequency. And that happens with some particular wavelengths and etc. And that also one have to figure out very accurately to make these neutral atom clocks which are based on optical lattices. So the optical lattices, to build these optical lattices, one have to use exactly that particular wavelength only, and that is called magic wave. Okay, so I'm almost at the end of my today's lecture. So now, I mean, I started basically with this plot only. So with all these things, today we have reached to an accuracy of few parts in 10 to the power minus 21 using neutral atoms for optical clock, and this is for ion is few parts in 10 to the power minus 9. So basically, you can see, one can say that neutral atoms are little bit even better compared to the iron clock, but that's not the limit. Actually, one can go even beyond. It's just the technical improvement in step by step. It's in today's date, neutral atoms are a little bit better than the iron clock, but maybe after a couple of months it can be changed. It will be probably changed. Okay, now let's see. So I actually discussed several techniques. In fact, I discussed only few techniques to you because it's a time constant and all these things. There are several other techniques which are used to build this kind of optical clocks or even any atomic. And these techniques are very, very sophisticated and complex techniques. So to build this kind of experiment, it's a fairly very complex process. It's not as complex as, let's say, LIGO. You are probably listening about LIGO or TMT and etc. etc. It's not that sort of complex, but it's fairly complex. And it takes very time consuming because most of the things have to be developed in the lab. And if you see the development process, it took several decades, starting from 1945 when Rabi first proposed the concept of the atomic clock. That was the time of Second World War. I think I discussed that part in my previous lecture. So since 1945, there are several milestones that scientists have achieved to build a clock which is accurate to like 1 second over 300 billion years. And these are something which I have written here. For example, the first cesium clock was produced during 1955. Then, based on that, the time was redefined with respect to atomic clock with respect in 1967. Earlier, before 1967, it was based on rotation of Earth. Then in 1993, this redefinition was again there was an amendment, and then it was based on cesium fountain, like cold cesium gas and fountain. In 2001, first optical clock was demonstrated. And today, let's say in 2014, no, sorry, that was the best fountain clock. And today we have reached to an optical clock which is some few parts in 10 to the power 21, which has lots of important applications in sophisticated technologies and science, which I will discuss in my next lectures. So just to tell you, like the techniques those are used to build atomic clocks have bagged several Nobel Prize, and you can see here 12 Nobel laureates. And for example, Rabi first introduced about the optical about the atomic clock. He got a Nobel Prize. Then Ramsey actually developed, Ramsey is actually Rabi's student, PhD student. So he developed the spectroscopic technique to measure this atomic clock frequency very accurately. It's called Ramsey spectroscopy. Then Demalt and Paul, today I talked about them, they developed the ion trapping techniques. Bill Phillips, Cohen Tanuji, and Steve Chu, they developed the laser cooling techniques and they got Nobel Prize in 1997. Laser cooling technique is used for cooling even neutral atoms or ions. Then Wineland, he further took these ions to make ion clock and quantum computers. So he got Nobel Prize in 2012. And Hansch and John Hall and Glauber, they developed several, which I did not discuss actually. They developed some quantum optics techniques, which is called optical frequency comb, which is used to measure these optical frequencies very, very accurately. So that part I did not discuss today. And they also got Nobel Prize in 2005. So what you can see, there are so many important discoveries had to happen to build this optical clock so accurate. Not an optical clock, let's say any atomic clock so accurately. There are so many important things that had happened. Okay, so then I am ending my lectures here. We know that presently there are several extremely high quality clocks. Now in next two lectures we'll be discussing why do we need these clocks. So the applications basically. So for that, please listen to my next two lectures. So I will end here. And now if there are questions, please let me know. Raise your hand, or I think maybe you are typing also. Are there any questions? So there are some question here. How do we calculate the stability of these clocks, ion, neutral atoms, etc.? So for stability calculation, it's a very good point. So if you have only one clock, you cannot measure the stability because that's a relative thing. So for stability, you have to compare at least three clocks at the same time. It's called a three-corner hat measurement. Even going into detail is very difficult at this moment, but the terminology is called basically three-corner hat measurement. So practically speaking, it's intercomparing different clocks which have same or similar, not same but similar accuracies. Then you intercompare them and then you measure a relative stability, not the absolute. Any specific reason to choose ytterbium? Question by Slok Shah. Yes. So ytterbium basically at IUCAA we want to build a atomic clock because we want to explore fundamental science using that, and that part actually I will discuss on my last lecture. And ytterbium is one of the most promising candidate for those fundamental science tests. So stick to my fourth lecture. I think you will learn more about that. So this is the reason why we want to do ytterbium. So there is one hand up, that is Vinisha Kalwani. So please, yeah,
Hello, sir. Can you hear me?
yeah.
So my question was, when you were talking about micromotion and circular motion, so can you observe micromotion visibly?
Yes, not visible, not by your own eyes, but you can measure them with
And so
precision
the
measure.
cause of the
Yeah.
cause of micromotion,
Sorry, what is the?
cause of micromotion.
The micromotions are coming due to the RF AC, alternating electric fields that you are applying. So the alternating electric fields are typically on the order of 10 to 100 megahertz frequencies. And that is modulating your secular frequency and gives the micromotion. So that these are the exactly at the same frequency as for the AC field that you apply.
Okay. And so the ion is trapped not by electrostatic confinement because Earnshaw's theorem prohibits that. So this alternating electric field, does it not produce a magnetic field?
Alternating electric field will produce a magnetic field, you are right, but you know that the magnitude of the magnetic field is some sort of, roughly speaking, the C, it's divided by C, right?
Yes, sir.
Electric field amplitude divided by C. And so that amplitude is so small, so that at the present accuracy level of clock, we don't care about that. So the magnetic field is so small, so the Zeeman shift will be very small, which doesn't affect in 10 to the power minus 21 level. It probably will affect in much when we can build much accurate clocks.
Okay, sir. Thank you.
Okay, so there is other questions here. If any event happen by if any event happens in specific fabric, sorry, space-time fabric, then it will affect how we perceive time on Earth. What accuracy clock should be used to detect that change in time? Will the clock based on ion trap technique be sufficient? Okay, so that's a good question, and that is actually what maybe you can I can defer you for my fourth lecture. So yes, you are right in one sense that optical clocks, well, not probably optical clocks, clocks will be able to detect this kind of perturbations in the fabric, space-time fabric. But yet, at this moment, with the present accuracy level of 10 to the power minus 21 and so, it's not good enough to measure that. So we need to measure even higher accurate clocks for that. And I can tell you, people are already trying different approaches using nuclear transitions and using highly charged ions, which probably will be few orders of magnitude better in accuracy, and maybe we'll have a chance to measure this kind of things. So basically, what you are trying to ask, whether we can measure gravity waves and etc. using clocks? Yes. So the answer is yes. So it will be possible, but only thing is, at this moment we don't have that sort of accurate clocks. There, Devamalla is asking, is in penning trap we have to consider Zeeman effect? So in Paul trap, why are we not considering Stark effect? And how do we connect the splitting? Because the Stark effect in ion trapping, actually we are considering, but that cancels out. If you look into the nature of the potential, it's x square plus y square minus 2z square, and it's symmetric in such a way that the Stark shift along x and y directions are same, and it is factor of 2 higher in the z direction. So what you do, basically you measure, you quantize the ion in 3 directions and measure the clock frequencies along 3 directions and average out, and then this shift basically cancels. But you are right, there is one. So I did not go into that sort of detail, because that will be like, will be, I mean, each of them are, then will take several classes. So Ajay Kumar is asking, any reference book you would like to suggest itself for study for clock? Yes, there are many very good, actually even not book, there are review articles you can read. There is one review article by PTP Germany called Guidelines for Building Optical Clocks. Otherwise, there is a very nice book on clock, atomic clock, which is by Fritz Riesel. You probably can also get an electronic copy of that. Soham Bose, can you please tell me how can we detect the number of ions in a single ion trap so that we can reduce the number of ions? Well, that's what I explained, that you just reduce the trap potentials and throw them one by one, then finally basically you will have nothing. So you calibrate your system in the fluorescence spectrum, and then next time you just stay when you have single ion. If the neutral atom has no net charge, then how are we kept trapped? Well, last time I was explaining the magneto-optical trap. So neutral atoms are not trapped in an ion trap. They are trapped in a magneto-optical trap. So maybe you can go back to my, I mean, in YouTube, you can go back to my previous lecture and listen the magneto-optical trapping part. That's what is used for trapping neutral atoms. Then I wanted to know that if these clocks have been developed by America and Japan, why are other countries like ours not able to make them yet? Is it because we are using different atomic species or unavailability of the exact designs? I want to understand the challenge we face compared to, okay, basically, okay. So basically the question is, that if US have done it, then why are we not able to do it? See, US have done many things, like they have a very high quality road, bullet trains, etc. But we are not able to do that. So exactly for the same reasons, we are not able to also. It's not that we are not able to do these things. It's like we have started very late. See, US have started in 1980s to develop these optical clocks, and it's true that they have developed each and every parts of it and from the scratch. We have started just, I mean, I started at IUCAA just 3 years back. Yeah, and these technologies are something you cannot buy from US and just put them together. You have to really build it yourself. For example, I need an iron trap. I cannot buy it from anywhere. I have to develop it in India, and that takes a lot of time. If I have to develop the entire, there are several other things which the details. So these building blocks have to be developed in the country. Most of them, they are not commercially available for different reasons. Even they have a strategic applications, so people don't sell it. So that is time consuming. That is one thing. That is the research part. But this assumes like you have enough resources available, like funding and other things. So those are also not adequate for different labs in India. So those are also bottlenecks. Yeah. So there are several reasons why basically we are lacking and etc. I hope I'm able to answer you. Okay, so is there any other question? I don't see anything online. I don't see anything in the Google document file. So if not, then let me finish here today and see you on the next lecture. Thank you.